From the planes we fly in to the cars we drive, we're trusting advanced materials with our lives every single day. They're built to be stronger, lighter, and better than anything that came before. But what if their biggest advantage, this layered way they're built, is also a secret invisible weakness? Let's dig in. So, a lot of these high-tech things, they're made from what we call composites. You can think of it like a kind of super advanced plywood, where layers of fibers are fused together. This layering is what gives them their incredible strength without all the weight. But it also creates a weak spot, one you can't even see from the outside.
And yeah, that hidden weakness, it's got a name: delamination. It's basically when the layers of a composite material just start peeling apart. And it doesn't start with some big bang or a crack you can see. Nope, it starts silently between the layers as a tiny fracture that can grow and grow until you have a catastrophic failure. This is the silent threat we're going to unpack.
Okay, so how does something that's supposed to be this strong just come apart? Well, it all boils down to the science of stress and how the forces you put on the outside create an absolute war on the inside.
Let's take a look at this simple L-shaped part. It's a total classic in engineering. Now, when you apply a load to it trying to close that bend, you're not just squishing the whole thing. What's really happening is you're kicking off this complex battle of forces deep inside the material itself. And here's the real kicker. The danger isn't the force you see being applied on the outside. It's these interlaminar stresses, these unseen forces that are literally trying to pull those layers apart from the inside out. Think about a deck of cards and trying to slide a card out from the middle. That's kind of the internal stress we're talking about here. Now, this is where it gets really cool because we can actually see those invisible forces. This is a stress map from a computer simulation. The blue areas are fine, they're being compressed, but look at that red. That is the high tension zone, the hot spot where the layers are getting pulled apart the hardest. This shows us exactly where a failure is most likely to begin. And the consequences of this are just staggering. An undetected delamination can slash the strength of a structure by as much as 60%. Just let that sink in for a second. That's like an airplane wing suddenly losing more than half its strength, all from a flaw you can't even see. So, if this damage is totally invisible, how in the world are we supposed to guard against it? Well, this is where engineering gets really, really clever. Instead of waiting for things to break, we can now predict that breaking point with incredible accuracy using something called a digital twin. So here's the playbook. First, engineers build a perfect virtual replica of a part. That's the digital twin. Then, they use a powerful simulation technique to hit this virtual model with all kinds of forces, way more intense than it would ever see in real life. This lets them find those red hotspots we saw before and actually pinpoint the exact location and the exact load where that first tiny crack will start. And the technology that makes this possible, it's a total game changer. The source material puts it perfectly. This method doesn't just predict where a crack will start, but it can also predict how it's going to grow. It's almost like having a crystal ball for material failure, letting engineers see exactly what will happen to a part under stress. Now, this isn't just a problem for huge aerospace parts. The very same physics applies on a completely different scale, inside the complex, microscopic world of electronics. We've seen how this invisible fracture can affect massive structures, but what about that incredibly complex, layered device that's probably in your pocket right now? Could your phone also be at risk of falling apart from the inside? You bet it is. The fundamental problem is exactly the same. It doesn't matter if it's a huge structural joint or the tiny printed circuit board in your phone, that risk of delamination is very real. But in the world of electronics, the culprit isn't a mechanical force, it's heat. See, when the electronics industry switched over to lead-free solder, which was a great move for the environment, they had to start using much higher temperatures during assembly. That intense heat can cause the epoxy holding the circuit board layers together to actually start breaking down, releasing gases and creating this huge internal pressure that can literally blow the layers apart from within. So for electronics designers, choosing the right material is everything. This table shows different types of materials and how long they can survive a crazy high temperature test at 288 degrees Celsius. You can see some materials just give up after 5 minutes, while others can hang on 3 times as long. This data is absolutely vital for making sure a device can survive the intense process of its own creation. And this all brings us to the real impact here. Understanding and predicting failure
isn't just some cool academic exercise. It fundamentally changes what's possible in engineering and design.
Because we can simulate and predict delamination before a single physical part is ever made, we can build things that are not only safer, but way more advanced. We can use lighter materials to make our cars and planes more fuel efficient, and we can do it with confidence, knowing they're structurally sound. We get to prevent the disaster before it ever has a chance to happen.
And that leaves us with a pretty incredible final thought. For centuries, engineering was about building things and then learning from how they broke. But now, we're stepping into a new era, one where we can understand and predict failure on a microscopic level before it even happens. So if we can see every invisible fracture before it forms, what does that mean for the future? What are the limits to what we can design, what we can build, and what we can achieve?